Welcome everyone to this masterclass explainer. I'll be your professor today, and together we're going to completely demystify MRI physics. I know, it's the topic that keeps grad students and radiology residents up at night, right? But trust me, by the time we wrap up here, you are going to have a rock-solid, structured understanding of exactly how we generate these incredible images. We're going to break down the physics step by step and essentially build you the ultimate exam review summary. So let's just jump right in. Okay, here is our syllabus for today. 1. The 5-step MRI journey. 2. Protons, spin, and resonance. 3. T1 and T2 relaxation. 4. Intrinsic spin versus extrinsic decay. 5. Controlling contrast with TR and TE. And finally, 6. Pathology and tissue contrast. Basically, we're moving systematically from the macro patient experience all the way down to the quantum level, so you are fully prepped for your exams. Section 1, the 5-step MRI journey. Now, before we even touch the quantum mechanics of it all, we really need to ground ourselves in the practical sequence of events. Just picture a patient in the scanner room going in for their very first MRI. There are 5 safe, foundational steps here that you absolutely must have memorized. First up, the scanner applies a massive external magnetic field, and this aligns the patient's protons. Second, we transmit energy into the patient using a radio frequency or RF pulse. Third, we just turn that pulse off. Fourth, and this is the wild part, as a direct reaction, the patient's body actually emits a magnetic signal right back to us. And finally, step 5, our receiver coil captures that signal and a computer translates it into the image we see. Top down, it really is just that elegantly simple. Moving right along to section 2, protons, spin, and resonance. So we've got the macro level checklist down, right? Let's zoom way into the micro level to see exactly how the machine interacts with the body to actually pull off those first 3 steps. I mean, just take a second to wrap your head around this number. 4 times 10 to the 27th power. That is roughly the number of protons inside the human body. It's astronomical. And because these protons have this quirky quantum mechanical property called spin, and because they're moving electrical charges, they effectively act as incredibly tiny magnets. Now, normally, these billions of tiny magnets are completely randomly aligned. They're pointing everywhere, so they just cancel each other out. Your body has 0 net magnetic field. But the moment we slide the patient into the MRI's incredibly strong external magnetic field, a small fraction of those 4 octillion protons actually align with the field, and that magnetizes the body just enough for us to work our magic. Now, once they're aligned, these protons don't just, sit there perfectly still. They actually start to perform this circular wobbly movement around the axis of the magnetic field. It's exactly like a spinning top that's gotten slightly tilted. We call this movement precession. And listen up, because for your exam, you absolutely must know that the speed of this wobble is called the Larmor frequency. To give you some real-world context, in a standard 1.5 Tesla clinical scanner, this frequency sits right at about 63.87 megahertz. So here's the crucial part. To get a readable signal, we have to forcefully push these protons out of their comfortable little alignment. And we do this by sending in our radio frequency pulse. But we can't just blast them with random energy. No, we have to use the exact Larmor frequency. Why? Resonance. Resonance is what allows us to highly efficiently transfer energy to the protons. It pushes their magnetization 90 degrees into what we call the transverse plane, which is exactly where our coils can actually measure them. Okay, this brings us to 2 incredibly helpful quantum analogies you're going to want to keep in your back pocket for exam day. First, think of that RF pulse like pushing a kid on a swing set. If you push at the exact right moment, the right frequency, meaning the Larmor frequency, you transfer energy perfectly, and that kid swings higher. That's resonance. Now, right after we push them, all the protons are spinning together perfectly, in sync. They're in phase. But the second we turn that RF pulse off, they start spreading out. And that brings us to analogy number 2, the marathon. Imagine a bunch of runners starting a race packed tightly together. Pretty quickly, they're going to spread out because, well, some run faster and some run slower, right? Our protons do the exact same thing. They quickly lose their phase coherence. Section 3, T1 and T2 relaxation. Let's see how all this builds into the literal core of image generation. Like, what exactly happens when we flip that radio frequency pulse off and let the protons relax back into their natural state? For the exam, definitely burn these key bullet points into your memory. You've got 2 independent processes happening at the exact same time here. T1 relaxation is all about longitudinal recovery. That's the protons slowly giving up their energy as heat to the surrounding environment, the lattice, to gradually return to their original alignment. T2 relaxation, on the flip side, is about transverse decay. This is our marathon. It's the much, much faster process of protons losing their phase coherence as they bump into and interact with each other's tiny magnetic fields. So just remember, T1 is recovery, T2 is decay.
Which brings us to section 4, intrinsic spin versus extrinsic decay. Now, T1 is usually fairly straightforward for most folks, but T2 decay? That one often trips up grad students. So let's take a closer look at the nuanced differences in transverse decay.
Look at the stark difference here between true intrinsic T2 decay and the much faster T2 star decay. True T2 decay is basically just those intrinsic spin-spin interactions. It's protons naturally falling out of phase simply because they happen to be near each other. It's just physics. It's unavoidable. But T2 star decay, that factors in the messy real world. It includes extrinsic factors, things like tiny microscopic imperfections in the MRI machine's magnetic field itself, plus random variations in the patient's own tissue, and those extrinsic factors speed up that dephasing process significantly.
Moving to section 5, controlling contrast with TR and TE. So we've talked through all these big physics concepts, right? T1 recovery, T2 decay, Larmor frequencies, but the million-dollar question is, how do we actually manipulate these physics to, say, differentiate a tumor from totally healthy tissue? Memorize this matrix. Seriously, commit it to memory for your exams. It shows us exactly how we can extract specific tissue characteristics just by tweaking the scanner's timing. So, repetition time, or TR, is the time between our pulse sequences. Using a short TR catches tissues while they are still vastly different in their T1 recovery. Echo time, or TE, is how long we wait to literally listen to the signal. A long TE gives those tissues plenty of time to dephase, which really highlights their T2 differences. So putting it together, a short TR plus a short TE gives you a T1 weighted image. A long TR plus a long TE gives you a T2 weighted image. And fun fact, if you use a long TR and a short TE, you essentially cancel out both of those effects and you're left looking purely at proton density. All right, final section, section 6, pathology and tissue contrast. Let's actually apply this synthesis to real-world diagnostics. Because honestly, understanding this physics matrix is really only useful if we can use it to help the patient sitting in front of us. So why exactly do different tissues show up as bright or dark on the screen? Well, it is all about their molecular environment. Fat molecules have this physical structure that lets them dump their energy into the surrounding lattice super efficiently. So fat recovers its longitudinal magnetization rapidly, which gives it a really bright signal on a T1 weighted sequence. Water, though, totally the opposite. Free water molecules hold onto their transverse phase coherence for a long time. They are the slow marathon runners from our earlier analogy. Because they retain that transverse magnetization so much longer, water appears very bright on a T2 weighted sequence. Okay, let me challenge you with a very classic exam question. If we purposefully design a sequence to be highly sensitive to that messy T2 star extrinsic decay we talked about, how does that actually help a radiologist find a really subtle brain hemorrhage? Well, think about what's inside blood. Blood hemoglobin contains iron, right? And iron is highly paramagnetic, which means it heavily distorts the local magnetic field around it. That local distortion massively accelerates the extrinsic dephasing of the nearby protons, causing this incredibly rapid signal drop-off. So, on a T2 star image, that hemorrhage is going to show up clear as day as a very, very dark spot. We're literally using the magnetic imperfections of the environment to our diagnostic advantage. It's brilliant.
All right, let's wrap up this masterclass explainer with a rapid-fire, top-down synthesis of your absolute must-know facts. B0, the main magnetic field, aligns the patient's protons. We use an RF pulse matched exactly to the Larmor frequency to hit resonance, remember the swing set, and flip that magnetization. When we turn the pulse off, T1 measures the slow, longitudinal thermal recovery. Meanwhile, T2 measures the fast, transverse phase loss, our marathon runners spreading out. And finally, you are the one controlling the image. Short repetition and echo times yield T1 contrast, while long repetition and echo times yield T2 contrast.
You guys now have the foundational MRI physics necessary to absolutely ace your exams and really excel in the reading room. But I want to leave you with a slightly broader, maybe more provocative thought to chew on.
We are literally using a giant magnet to listen to the quantum radio broadcasts of octillions of protons inside a living human being and doing it perfectly harmlessly. If we can manipulate atomic spins to safely peer inside the human body like this today, what other invisible quantum phenomena are just waiting out there to be harnessed for the future of medical diagnostics? Think about it. Thank you so much for joining me for this explainer. Study hard, and I'll see you in the next masterclass.